So I decided to just record this bit of lecture for you guys so that we don't have to do this tomorrow. The only thing on this that I'll worry about testing you on is nodes. Everything else I won't bother with since it's not particularly important to 90% of you anyways. But you should watch it anyways for the sake of the storyline. So we talked about this in class last time. We started with waves, we went to matter as waves, and then we've almost finished electrons as waves, but not quite. We need to talk about how we can put them into models as well. That's what we're going to do in this podcast. The reason that this is important to most of you is that it builds the story of how we get to orbitals. The math is not particularly important. The model itself is really just useful to you guys for the sake of seeing how it turns into orbitals, and that's it. Now, if you are a chem major or a chemical engineer, that's not true. You guys need to watch the other podcast that goes into this in more detail. I already told you that it's mandatory. So continuing with what we talked about in class, we have a box. And it's not a literal box, but we have a situation where a particle is stuck and cannot get out. This first model that we're looking at is just a two-dimensional box. So if you were thinking of it as a particle, it could go back and forth. But it's not a particle, it's a wave. So instead what it does is we can think of it as an equation. And the equation is going to have energy levels. We'll show you that in a second. But it's going to take different states. So I have these drawn out here. So at its lowest state, it would look something like that. Now notice if you look at this, it looks like a sine or a cosine wave. We put them in terms of sine, so we'll call it a sine wave. If it increases in energy, it then becomes something that looks like this. Again, it's like a sine wave. But now, instead of just going through here, it keeps going and you have this as well. You go up another energy level and, well, you get the pattern. You just add in another peak. And so these are your different energy levels. These are your different states that if you put an electron inside a box that it cannot get out of, and that's what this part here means. It just means that you can't let the electron out. This is what happens. You can look at this and say, oh, we've graphed these things before, not in our class, but in algebra, trigonometry, whatever classes you had that taught you math. And we could explain that with an equation. And of course that's true. Let's give this equation a name because it's a particularly important equation. And so we're going to call it psi. And psi is what we call the wave function. This should not be a scary name, just break up the word. Wave function. It's a function that describes a wave. And in this particular case, called psi. So psi describes the movement of a particle. It describes that picture I showed you in the last slide. It's just a symbol for an equation. Don't let the fact that it happens to be a Greek letter that we don't use regularly bother you. It's just a psi. Every particle is going to have a different psi, or at least every type of particle, I should say. So an electron has a psi, an electron in a two-dimensional box has one psi, an electron in a three-dimensional box has a different. I'll show you that in a second. And an electron that's around a hydrogen atom has a different one. Each one of these has different equations that it describes since it's describing its movement. And its movement is going to be changed based on the situation that it is in. So psi squared is your probability density. We're not going to go into the mathematics of this too much, but just look at the word. It's probability density. So it gives us some idea of where the particle is. So if you look at psi squared, it's over here. It is just whatever psi was, the red line, squared. Now, it's a probability, so it's always going to be positive. And you can see that that's true because once the wave function becomes negative, when you square it, it's now positive. And so psi squared, wherever your 0 is, will always be positive. It gives us the probability of finding the particle within a region. And from a technicality standpoint, it's the probability of finding a particle divided by the volume, but we're not going to worry about that either. So we can look at it and say, okay, well, at this highest peak right here and right here, that's our most likely spot to find an electron. Right here in the middle is 0. There is no probability of finding the electron there. And this is a special spot. It's called a node. So whenever your wave function equals 0, your psi squared, or your probability density, is also going to equal 0. So the probability of finding the electron there is none. So that's called a node. It occurs when psi is 0. And remember, this is the only part of this video I'm testing you on, so you will be expected to know it, and you will be expected to expand it when we get to the hydrogen atom. So this happens when our psi is equal to 0, which makes our psi squared also equal to 0. And I've said this a couple of times already, but what does that mean about the probability that the electron is at a node? If its probability density is 0, that means it is 0%, or it won't be there, ever. Now notice, that means that the electron can be here, and here, and here, and here, but never, ever, 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 ever here. So it gets from here to here without ever going through the middle. That's kind of interesting. As a trick to remember for the particle in the box, wave functions are always going to have n-1 nodes. So if you're at energy level 554, it's going to have 553 nodes. Generally, we're only going to be talking about energy levels up to 5 or 6 or so, but it holds for the rest of them as well. Okay, so let's answer this question. At the node, which of the following is true? Is the electron likely to be there? Is the electron unlikely to be there? The electron will never be there, or it doesn't tell us anything about where the electron is. This is a trick question. Hopefully you got that the electron will never ever be there. Remember, 0% chance. It's not going to be there. So if you said unlikely, you were close, but it's really, really, really never going to be there. And when we talk about the hydrogen atom, that's going to be true in a couple of different places, especially the nucleus. So make sure that you keep that in mind, that while we're talking about it right now in terms of particle in the box, this will hold for all the rest of our wave functions as well. So this slide is generally where students get a hazy glaze over their eyes and stop paying attention to me. But bear with me on this. Psi is just an equation. We know it's just an equation. We also know what it looks like already. So I've showed you what it looks like already. And we've already declared that it looks like a sine wave. Well, notice what this is. It's just an equation that has a sign in it. And so it has a bunch of other numbers too, but most of these are constants. Hopefully you know what the number 2 is. It's right here. Self-explanatory. L is also going to be a constant that you would be given or that you would have designed in the experimental setup, something like that. It's the length of the box. So however big the box is going to be L. Now N is going to be your energy level. So that too is going to effectively be a constant because you're going to know what energy level you happen to care about. Or maybe you care about 2 energy levels and you're going to do a transition, something of that sort. But you're going to know what N is. You're going to know what you care about. Or the problem will tell you what to care about. Pi, I think you guys got that one too, just a number. We have L again, same thing, length of the box. And then we just have our variable, which is our X, or our position along the number line. Now, I'll show you in class briefly where these actually come from. These are solutions to a differential equation. Obviously, we're not going to do differential equations in class. A lot of you are still in calculus. However, once you have this wave function, you can fill it into a very important equation called the Schrodinger equation. And all this means, and if you want a much longer version of this, go see the other podcast. It walks through a couple of these for you if this is something that interests you. But basically it says, okay, if you take and you have something called an operator and you operate on this equation, you get another number out, and that's our energy. We're not going to go into too depth in this unless you happen to care and go watch the other video. When we solve this differential equation, we come up with an energy value. They're all constants. We know our L, we know our N. Our mass is or our M is our mass, so we know that. We know what H is. And this tells us our energy levels. So if we want to calculate the energy level of N equals 1, we fill 1 into here. We fill in our H. We fill in the mass of the electron and the length of the box that we're looking for. This is actually a relatively important model that they use in organic when you're talking about conjugated dyes. So keep that in mind when you're learning inorganic, but you usually don't go into particle in the box in organic either. The next place you'll likely see this is in physical chemistry if you take that. So we're going to expand this out into 3 dimensions real quick. I'm not going to actually show you the equation because it gets a little bit even hairier than this, but I do want to show you the picture because it looks cool. So if you graph a three-dimensional particle in the box, it just looks like this. Notice you still have your sine waves. If we're pretty good at calculus and looking at pictures and coming up with the equations for it, you can see where there's kind of the sine wave here, the sine wave here. But I really just wanted to show you the picture to say, hey, look, we can extend this to 3 dimensions. This basic idea, this basic principle is also how the hydrogen atom is solved for. It's how approximations on other atoms are solved for. It's all using the Schrodinger equation and differential equations to find the wave function and the energy value. We're not going to solve for those though, we're just going to tell them to you. And in the case of the hydrogen atom, we're not even going to show you the wave function per se, we're just going to show you the pictures. And those you've already seen. You know what s orbitals look like, you know what d orbitals look like from high school. And if you don't, you're going to go review that before we start talking about it in class. But we'll review it in class as well.